Okay, so thank you, Ken, for the nice introduction, and thanks for having me. As Ken said, I'm new here, so I'm very excited for the opportunity today to present my research, and hopefully will lead to further collaborations with people at the IA here. So today, my plan is to divide the talk into 3 different topics, very interconnected. And first, I will talk about the chemistry in the interstellar medium, and in particularly in a low-metallicity environment. And the second part of the talk, I'll talk about how dust evolution will affect the chemistry in these low-metallicity ISM. And finally, if time permits, I will talk about our ongoing work about the origin of molecular outflows. Okay, so first of all, before we even talk about low metallicity, let's talk about the motivation. Like, why do we care about the chemistry in the ISM? To me, the main reason to study chemistry is because of the fact that molecular clouds are the place for star formation. So we know that if we look at the molecular clouds in our Milky Way, or even if you look at nearby galaxies, you see star formation almost exclusively occurs in molecular clouds. And the dominant chemical species is the molecular hydrogen, or H2. So this is a seminal paper by Miguel et al. Almost 2 decades ago. So looking at nearby spiral galaxies, you can see if you look at their distribution, you can very easily pick up the strong correlation between H2 and star formation. On the other hand, if you look at the atomic hydrogen, you see that they're almost uncorrelated. And this leads to the so-called Kennica-Schmidt relation, which relates the star formation surface density to the gas surface density. And here, this is the H2 gas surface density. If you look at H2, you see a very nice linear correlation between the two, which suggests that there's a constant timescale of gas depletion. So which defined as follows, it's around 2 gigayears, which tells us that if you have, for the given amount of H2, it's able to sustain star formation for roughly this timescale. On the other hand, if you look at atomic hydrogen, you see almost no correlation. But so unfortunately, we cannot actually observe H2 because H2 is actually invisible. It's not a very efficient emitter in typical condition in molecular clouds because the temperature is too cold. And the main reason is because that H2, the atomic weight of H2 is very low. That's actually more important than the lack of dipole moment. So you need to go to a much higher temperature to excite H2 and see that emission from H2 directly. So in order to infer how much H2 there is, observationally we need a tracer. And the most commonly used tracer is carbon monoxide, CO. And this is the brightest lines in molecular clouds. And if you look at nearby galaxies, you see this very bright CO map tracing the spiral arms where most of the star formation occurs. Now, to understand why CO is a good tracer for star formation, for H2, we first have to have a brief recap on the ISM chemistry. So we know that in the galaxy there's diffuse gas of H1, the atomic hydrogen, and this diffuse H1 is embedded in this constant radiation field from, not constant, but the 5eV radiation field from young stars. And it turns out that this 5eV radiation is very efficiently destroy H2 by the so-called photodissociation. So that's why in the majority of the volume of the ISM, the gas is atomic. However, if you go to the dense gas if you accumulate enough column density, then it turns out you can block out this UV radiation both by dust shielding and by the so-called H2 self-shielding. So H2 can self-shield itself, and it can provide a protection. And in the inner part, you start to see the formation of H2. And the formation channel, the most important channel is the H2 formation on dust grains. Actually, there's also the gas phase channel for H2 formation, but it turns out that this is like orders of magnitude less efficient compared to the dust phase. So in the Milky Way, or at solar metallicity, the formation on dust grains is the dominant formation channels. And the transition from H1 to H2 is actually a balance between the H2 photodissociation and the formation of H2 on the surface of dust grains. Now, if you go to even denser part of the cloud, first of all, in the diffuse ISM, this UV radiation, the same UV radiation, is able to photoionize carbon. So in the diffuse ISM, we'll see this carbon in the face of C+. But if we go to even denser part of the cloud, once you have enough shielding by dust, you'll start to see the transition from C+ to C1, or the atomic carbon. And this is, again, very similarly, depending on the balance between photoionization and the recombination to carbon. And once you go to even denser part, you start to see CO. So again, it's also similar. CO will be easily destroyed by far UV radiation. And the formation is actually, the formation of CO actually is in gas phase. So it doesn't explicitly require the existence of dust. However, it implicitly, depending on that, because the formation of CO requires the existence of H2. So the formation channel, you see there's a lot of reaction here, and this chain of reactions relies on the existence of H2. So in that sense, H2 formation also depends on the amount of dust you have. And this, because of this, we expect, theoretically, we expect CO is a good tracer, spatially, tracing the amount of H2. So all this is well and good for spiral galaxies. However, things become weird if we look at dwarf galaxies. Now, if you look at the star formation rate as a function of, if you look at the star formation rate per CO luminosity, so given the same amount of CO luminosity, dwarf galaxies seem to be have much higher star formation rate. And the most naive, simplest explanation is that these galaxies are forming stars like crazy, because you give them just a tiny bit of CO, and they're able to form a lot of new stars. So that would be the most naive explanations. However, another thing we have to notice is that dwarf galaxies, they also tend to have low metallicity, so they're metal poor. And as it turns out, the chemistry at low metallicity is very different from like solar metallicity environments. This seems to be a trivial statement, because after all, CO is made of carbon, and carbon is metal. So obviously, at lower metallicity, you naturally have less carbon, right? But it's, in addition to that, there's also the chemistry aspect, in a sense that if you're in a metal-poor environment, you're also bound to have less dust, right? Because dust is made of metals. So, which means that you'll get less shielding. The radiation shielding will be less efficient by dust. And this far UV starlight will therefore penetrate deeper into the clouds. So if you look at the same structure that we've seen previous slides, you'll see the surfaces of CO1 and CO would shrink very rapidly as you go down with metallicity. And at some point, it just disappears, which is why it's so difficult to observe CO in dwarf galaxies. On the other hand, if you look at H2 in theoretical models, it also shrinks, but not to the same extent. And this is due to the fact that H2 is able to do self-shield. So the H2, the existence of H2 itself is able to provide a protection against the far UV radiation. So this leads to the so-called CO dark gas, is that theoretically we might expect at low metallicity there might be still a lot of H2, but we just don't see that much CO, which explains why these dwarf galaxies have such a high star formation rate to CO luminosity ratios. Because it's not because they are forming stars very efficiently, it's just because it's very difficult to form CO at low metallicities. So if you account for the so-called CO dark H2 gas, then you can put this dwarf galaxy back to the Kennicutt-Schmidt relation in a sense that there's actually a lot more H2 for the observed level of CO. You can see once you take that into account, you go back to the Begiel et al. Like this linear correlation on the Kennicutt-Schmidt plane. Right. So this seems to be a very nice explanation. But the question is there really a lot of H2? Now, we also know that in a talk, it's often the case that if the speaker asks a question, the answer is always no. I'm going to spoil that and tell you that the answer is no, and I'm going to explain right now. Oh, as an important aside, the importance of low metallicity galaxies is not just for us to understand dwarf galaxies, which is by itself already a very important, a very interesting topic, but there's also interesting connection to the high redshift galaxies, because as the JWST discovered all these galaxies at extremely high redshifts, we start to realize that these high redshift galaxies have very low metallicities, comparable to local dwarf galaxies. And if you also look at the distribution of those high redshift galaxies, you see blobs, and one blob represents one galaxy, because there's just no spatial resolution to resolve these very high redshift galaxies. So dwarf galaxy is actually a great place for us to understand low metallicity ISM in great details. Now, there are a handful of nearby dwarf galaxies that turn out to have successful CO detection. So most of the dwarf galaxies, if you point your telescope to those galaxies, you see non-detection. But they are actually just two. So there are two galaxies I know of with a low metallicity, like at the order of 0.1 solar metallicity, that has successful CO detection by ALMA. And this particular galaxy is called WLM, dwarf galaxy. You can see on this map here, these black contours represent the CO clumps detected by ALMA. And they are tiny, they are very compact, like parsec scale, each of them. This is much smaller compared to like in our Milky Way or in spiral galaxies. And this fits our theoretical model, right? Because as we just talked about, CO would naturally shrink to tiny cores. But if you want to study it using numerical simulations, the implication is that you need very high resolution. Right? You need at least parsec scale, if not smaller, to resolve these parsec scale clumps. So to study the metallicity effect, we run a simulation of a so-called ISM patch simulation, where you simulate a parsec scale patch of a size of 1 kiloparsec, and the boundary is periodic boundaries in x and y directions, but horizontally along the line of sight direction. And the horizontal vertical size of the box is actually very elongated, so you can also study how gas, the outflow of gas, and how gas leaves the galaxy by stellar feedback. Now, for those of you who care about the simulation details, these are how we do the simulations. So we use the Gizmo code, which is a Lagrangian code using the MFM solver. And the simulation is coupled with a non-equilibrium chemistry network that follows the hydrogen chemistry, which means that we can study H2, H+, and H1 on the fly. So we can capture the non-equilibrium effect. Now, if you want to do chemistry, you need to have a treatment for radiation shielding. In our simulation, we're using the so-called Hillpix-based method, in that for every gas particle, we define a sphere to look for its column density. And each sphere, we actually define a Hillpix tessellation of 12 different sight lines, so that we can calculate the column density along these different sight lines. And this gives us a good proxy of the column density responsible for radiation shielding. And there's also star formation with individual stars. And by that, I mean that because our resolution is at a scale of solar mass scale. So each particle is 1 solar mass, and which means that it's no longer, it doesn't make sense to assume that one particle represents a stellar population, right? So what we do is that we use the stochastic method to sample the stellar IMF, to sample the location of the massive stars that will eventually be responsible for stellar feedback. So here is an example of that simulations. You can see each circle represents a massive stars, more massive than A solar masses, and the size represents its mass. So the larger the circle, the more massive they are. Finally, we include stellar feedback, both the supernova explosion and the photoionization. And this would naturally give us all these supernova or feedback-driven bubbles, and which will also regulate star formation and will give us a hierarchical turbulence structure in the ISM. So I just told you that we have hydrogen chemistry network in a simulation. However, in order to study CO, we also need carbon chemistry. But the difficulty in simulating carbon chemistry is that carbon chemistry is a much larger chemistry network. You can see a lot of chemistry species involved, and actually hundreds of chemical reactions. So that's very expensive. But we also need to remain very high resolution if we want to resolve all these parsec scale CO clumps. So that's a challenge, and previous method either adopt a simplified CO network. By that I mean that you just get rid of those some species that you think are not relevant, and you have a much smaller network to run. And the advantage is that this gives you a very fast network. But however, it's hard to devise a accurate simplified network. So one of the most popular simplified networks is the so-called Nelson and Langer 1997 model, which we know that it tends to overproduce CEO. The other method is to do it in post-processing. But the disadvantage of doing so is that in post-processing, because you're not doing the same thing on the fly, you have to assume chemical equilibrium, or assume the chemistry is already reaches a steady state. So what our method is that we're doing a hybrid method, in the sense that we still run the hydrogen chemistry network on the fly in a simulation, so we can get all these H+, H1, and H2 in a simulation. And then we do post-processing. But the important thing here is that we're using the non-equilibrium chemical abundances as input to calculate the rest, the carbon chemistry. So this is very important because we want to capture the non-equilibrium effect of H2. And why is that so important? It's because H2 is almost never in chemical equilibrium. The reason being that H2 formation is very inefficient. So the formation timescale goes like this. It's 1 gigayear over the hydrogen number density and the metallicity. And if you have solar metallicity at a density of 100 particles per cc, the timescale is 10 million years, which is already not short. So it's already comparable to typical lifetime of molecular clouds. Now imagine if you now have 10 times less metals, that means 10 times longer timescales. Your formation timescale becomes 100 million years, which means that you have to wait for 100 million years for the H2 to grow from 0 to its equilibrium abundance. And in a dynamic time ISM, there's just no time, because we don't expect the cloud lifetime to explicitly depends on metallicity. So if you look at the simulation, chemistry species as a function of the H2 abundance as a function of density at different metallicities, you realize that it's almost underabundant. So these solid lines represent the non-equilibrium chemical abundances, while the dashed line represents the fully steady-state chemistry prediction. And the difference becomes the most pronounced at the lowest metallicity, because that's where H2 formation is the least efficient. And you can see this like orders of magnitude difference in the abundance. And this tells us that if you consider the non-equilibrium or time-dependent effect, the start forming the cold phase in the at low metallicity is actually H1 dominated instead of H2 dominated. Well, I basically just said that. So if you consider the non-equilibrium effect, you'll see that it will give you a 10 times less abundant H2 at 0.1 solar metallicity. And this has interesting implications if you look at the column density of clouds of H2 versus CO. And in the Milky Way, we have some observational data by absorption. And we can directly compare that with simulation models. So the fully steady-state model will predict something like the blue line, while the orange line represents our time-dependent simulation. And you see that the steady-state model will overproduce H2, which shift the line to the right and away from the observation data. Now, so far we've seen the chemical species, but to compare with observations, we also have to do radiance transfer. We have to predict the observables. So we did radiance transfer using the RADMC 3D code, do a fully non-LTE calculation assuming a large velocity gradient and make predictions of the CO lines. With that, we can start to calculate the so-called CO to H2 conversion factor, or XCO, defined as the amount of H2 divided by the CO intensity. And so some previous observations estimate the XCO as a function of metallicity as these lines. And this turns out to be overestimation because of the assumption they made. So there are two approaches to do. You can do that. The first approach is to do a PDR modeling. To run some chemistry, assuming a steady state assumption, and what you will get is that you will overestimate H2 as we've seen, and this gives you a too high XCO at low metallicity. And another way people do this is to use the so-called inverse Kennecke-Schmidt law, in that it's using the information of the star formation rate, and then assume the depletion time is always 2 gigayears. And then with that you can calculate the H2 mass. This is also not a good assumption, because as we just saw, this star formation reservoir is actually dominated by H1 instead of H2. So our predictions is actually flatter. The time-dependent fiducial model is actually much flatter than other observational estimates. Okay. Yeah, so I'm going to the second part of my talk about dust evolution. So what do I mean by dust evolution? So, well, as we've seen, dust plays a key role in the ISM chemistry, both because of shielding and because the formation of H2 relies on dust. But most studies, most simulations, assume the constant dust-to-gas ratio. However, if you look at real galaxies, for example, in the SMC, you see that the dust-to-gas ratio actually varies from place to place. And this is actually sort of expected, because we know there are processes that can destroy dust, for example, like supernova shocks. And there are also processes that can create or form more dust, for example, by accretion. So this is actually a natural consequence, that the dust abundance or dust-to-gas ratio is not a constant. And the variation can be as much as the factor of 7. So if we believe that dust is important for chemistry, we have to take that into account. So in this project, we simulate a dwarf galaxy, very similar parameters to the WLM galaxies. And now we include the dust destruction in supernova shocks and dust growth or accretion in cold ISM. And we couple that in the chemistry network. But before I show you the results, actually, I forgot to explain this. This is the H1, H2, and H plus map we just saw. And here is temperature. You can see all these hot gas generated by supernova feedback. And here is the dust to gas ratio. And as you can see, there's this like concentration of dense clumps. So the dust to gas ratio is actually elevated in these dense clumps. So before I go into the results, I first want to explain what we included in our dust evolution model. The first is that we have dust destruction by sputtering. And sputtering happens because of collision between dust and gas. And it has to be the relative velocity has to be very high in order for the gas particle to kind of kick, like eject a dust material on that. So you destroy dust. This happens at high temperature. So you can see that the sputtering rate or the erosion rate is actually a sharp function of density of temperature. So below 10 to the 6 Kelvin or so, there's almost no sputtering. But once the gas temperature is hot enough, you start to see very significant sputtering. And we also include non-thermal sputtering, which basically means that if there's coherent motion, it's not the thermal velocity, but the large-scale velocity between gas and dust. It can also lead to sputtering. But on the other hand, there's also formation of dust, and we include the so-called dust growth. And this is also collision between gas and dust, but it happens in the cold phase. So this happens when the velocity is not so high, such that the gas phase metals can actually stick onto the surface of dust. So it's actually a creation process of dust. Now, if we run the simulations, if we look at the tiny evolution of the total H2 mass, you'll see that it actually doesn't really care about dust evolution for H2. But for CO luminosity, it cares a lot about dust evolution. There's an order of magnitude difference in CO luminosity. It's basically saying that without dust evolution, you actually see no CO at all, almost no CO. And the reason is, it is mainly a consequence of dust growth. If we look at the chemical abundance as a function of density, we'll see that if we look at dust, we will see without dust evolution, this will be a constant. But once we include dust growth, you see the dust abundance will just naturally increase at higher densities and then saturate at some fixed values. And this will lead to a slight increase of H2 abundance, but the effect is not strong. The reason is that H2 itself can already self-shield. So it doesn't rely on the shielding by dust. But on the other hand, CO or the carbon chemistry is actually very sensitive to dust evolution. And that's because CO is not able to efficiently self-shield. Okay, let me skip this. So if you look at how the dust to gas ratio is measured or inferred observationally, basically just measuring the amount of dust and gas separately, and then you take their ratio. Okay. Now, this is all fine. So you measure maybe you measure the dust continuum, and then you also measure like 21 centimeter, and you get H1. And the problem is the H2. You just don't know how much H2 there is, right? So usually what people do is obviously you measure some CO luminosity, and then you use a conversion factor. So alpha CO is just another version of XCO times some constant. So there's a lot of uncertainty here, and as we argue that if we consider dynamical effect, the XCO actually is much lower because there's not that much H2. So if you use the conventional like very steeply rising XCO, you're bound to overestimate the amount of H2 at low metallicity, which in turn will lead to underestimation of the dust to gas ratio. So the bottom line is, in a metal poor environment, the ISM is bound to be H1 dominated. Okay, good. So I still have a bit of time. I want to switch gear, then talk about molecular outflows. And this is ongoing work, and so take this with a grain of salt. But the motivation is that we see them. So they are molecular gas in galactic outflows. So galactic outflows are gas being ejected out of galaxies by stellar feedback. And in like local starburst galaxies, sometimes we see them. For example, here you see these contours here. These are CO emission. And here's another example. Both of these are starburst galaxies nearby. You see these contours are just CO clouds, and they are very far away from the galaxy, which is hard to understand because, oh, by the way, also there are also evidence that this seems to be very common at high redshift. But this is actually very puzzling because if you think about a cloud being pushed away by stellar feedback, and if you calculate their Kelvin-Helmholtz timescales, it's actually very short. So theoretically, we would expect that clouds should be destroyed just by fluid instability very quickly. But somehow we still see them. So this has been very puzzling until people realize that actually cooling can help a ton. So if you ignore cooling, then the cloud a cloud traveling in a hot tunnel or a hot gas pushing a initially static cloud will dissolve in a so-called cloud crushing time, or the Kelvin-Helmholtz timescale. However, if you include cooling, if cooling is efficient, which means that it's either in a dense environment or your cloud is large enough, then the competition between cooling and instability determines the outcome. When the cooling is more efficient, not only do these clouds survive, they can actually grow just by accreting from the hot gas. So the hot gas will cool, and then because they need to reach pressure equilibrium, so they will accrete to that cold cloud, and the cold cloud actually grow in size, in mass. So this is shown in this paper by Granco and O, 2018. That it actually just depends on the ratio of cooling time versus to the cloud crushing time. But it actually doesn't solve the problem entirely if you think of how H2 is formed. Because in order to understand why we see H2 in outflows, we still need to answer these questions. First of all, these clouds, these simulations, so these clouds are actually at a much higher temperature. These are around 10 to the 4 Kelvin. But we know that H2 formation occurs at much lower temperature because otherwise hydrogen will not be able to efficiently stick on the surface of the grains. And the second question is that, as we already seen, H2 formation happens on dust grains. If you destroy all the dust, then there's no dust to form. There's no surface to form. So the question is, can dust survive sputtering? Because in the hot gas, sputtering should be very efficient. And it seems to be yes. So because observationally, there are evidence that we see dust outside of galaxies. For example, if there are emissions using, I think, Herschel data, you can directly see the emission from dust. Or if you use reddening, you use extinction, you can also infer that there is actually a lot of dust outside of galaxies in a circular galactic medium. So dust can survive, but how? Because as we just mentioned, sputtering at high temperature is actually very efficient. So to understand this, we happen to have an ideal code to study this problem. So we run the same so-called cloud crashing simulations, and now with our dust evolving chemistry network. Simulations is a typical cloud crashing simulation that we start with a cloud here, or initially static, and then we have hot gas traveling this direction and sort of mimicking the stellar feedback from here, pushing this cold cloud away from the galaxy. And you can see that at a few cloud crushing timescales, so at 2 cloud crushing timescales, you see this dense gas here, the tiny dense red thing here. But this is temporary, so this will be destroyed very quickly. But the tail is actually what eventually leads to the accretion because of cooling, as we just mentioned. When cooling is efficient, you develop this tail by accreting the hot gas material. And the important thing here is that if you look at the structure of these clouds, it's actually not just a single phase. It's roughly we can call it a 2-phase cloud because there is the warm phase at roughly 10 to the 4 Kelvin, and there's also this like bluish part which is a cold phase. So this explains how you actually form H2. So potentially you can form H2 there because the temperature is low enough.
So Chia-Yu, when you do the simulation, do you set that initial hydro-equilibrium condition?
Initially, it's in pressure equilibrium. Right. So as I said, the cloud would naturally develop into this 2-phase structure, which is very similar to the case in the ISM. Right? We have the warm neutral medium and the cold neutral medium, and they're roughly in pressure equilibrium. It's just by the nature of cooling and the cooling curves, naturally develop into this 2-phase structure. So you can see the time evolution at different times, and you see these 2 peaks at 2 different densities. So this first peak, so the first peak here this is just the hot gas, and the second peak in the middle, this is the background, the warm phase, and then there's this third phase. This is the cold phase, which is what we want. And so you can see the same structure if you look at the temperature distribution or the phase diagram. Now, if we look at the dust to gas ratio as a function of time, we'll see that dust extraction almost all the dust extraction occur in the hot phase. So actually this is probably more clear in this map here. So this is the surface density of the gas compared to the surface density of dust. And by comparison, you see that there's almost no dust outside of the cloud because sputtering in the hot phase is super efficient. But the thing is, because of accretion, the material accrete onto the cloud later on is already dust free. So the accretion itself will eventually dilute your dust to gas ratio, right? It doesn't necessarily destroy the existing dust in the cloud, but it will suppress the dust to gas ratio, which is what you can see when we switch off dust growth, the green line here. So it drops as the accretion because of accretion from the hot phase. So this is not good for H2 formation because we want a lot of dust. So this is when dust grows to the rescue, because if we now consider dust growth, which is the solid blue line here, and suddenly we can reform this dust or just form more dust. Just look at this panel here. So without dust growth, this dilution effect will just very rapidly suppress the dust to gas ratio. But if you allow dust to accrete in the cold phase, then the dust to gas ratio actually boosted by orders of magnitude. I'll skip this. And now we're in business. So because of dust growth, they're actually the ideal site for H2 formation is actually in the cold phase, right? Because of dust growth, there's new dust being created in this cold phase, which will eventually lead to, like, if we look at the blue line here, leads to the formation of H2 at later times. And this is when if we switch back to the previous slides, and this happens once the dust to gas ratio is boosted by dust growth. Okay, so in summary, I have three takeaway messages. First of all, there's not much CO dark H2 gas at low metallicity because of timescale argument. And secondly, the observed CO luminosity requires us to consider dust evolution, and in particular dust growth, because you need that elevated dust abundance in a dense phase. And finally, dust growth is also able to explain the observed molecular outflow, because without that, the dust gas ratio in the cloud would simply be too low due to the dilution by the dust-free hot gas. Thank you.
Great talk. I have two questions. First one is, in the outflow, so the dust is forming there. Do you know what's happening to these clouds in the end? Are they being reaccreted into the galaxy, or are they?
This cannot be answered with our simulation setup. So this will require global galaxy simulations, as I showed previously. But not only that, it also requires an insane amount of resolution, because the motivation to do this in such an idealized setup is that we cannot resolve the cloud very nice and properly if we run a full disk simulation. Yeah.
All right, and second question, if I may. Can you say anything about C+ as a molecular gas mass based on your simulation?
Right, sure. So we actually have a paper out about C+, but I didn't show it here. So we also look into C+, and it turns out that it's kind of a tracer for H2, or even not really necessarily H2, because we form very little H2 at low metallicity, but it is a good tracer for star formation because of you need high density to excite, collision excite C+, right? But there is a clear metallicity dependence as we found in the simulation, which is actually also expected due to the fact that you naturally have less C+. Right? So the trend is there, but the normalization is metallicity dependent.
Okay, similar to CO in that sense.
Yep, but less so, because for CO you just don't see it.
Yeah, thanks.
I remember years ago people talk about dust will be preferentially blew away by radiation pressure, even from
Right.
galaxies. As you indicated, in some case, blew away far from the disk of galaxies. So in your treatment, now you talk about dust to gas ratio. Whether locally it could be important. You talk about this ratio will be kind of radiation pressure in star-forming regions will preferentially blow dust away.
Okay, so first of all, this cannot be, so we cannot address this this question, because our treatment is essentially a passive scatter treatment. So we don't separate dust from the gas fluid. But physically, I think people, so there was a time that people think that radiative pressure from dust is super important to drive like outflows. But I think this kind of faded in recent years in the sense that now people only believe that this is an important mechanism in like very high surface density environment. Because there's not, because for that to be efficient, you need like rescattering, right? The single scattering from UV light is not inefficient to push dust grains like significantly. So it requires a re-emission in the infrared to kind of boost that momentum driven momentum boost factor, and that's I think this current consensus is that it's only efficient if the surface density is high, like in starburst environment, for example. Well, definitely not in the like dust poor, like metal poor environment. I think it's negligible.
Anyway, and Ida in PC.
Thank you for your talk. Would you mind going to the conclusion? So I want to make sure I understand the conclusion of the first part.
Right.
So you mentioned that the conversion factor could be overestimated before, but then with your new treatment, it seems like that the H2 mass could actually go down.
Right. So I think.
Going down, yes. So that means the star formation efficiency for drop analysis is deviate from calculation again.
Yeah. So okay. I get your point. So I think it's not that there's no. Okay. I think the short answer is that the star formation, the definition of star formation efficiency, if you use H2, it's actually misleading in this context because we're saying that you don't need H2 to form stars. That's our central assumption, right? So in our case, the cold and dense gas is actually dominated by H1, right? So the formation of stars is not tied to the existence of H2. So if you then look at the depletion time of the total gas, then it's the same, it's normal, right? But if you believe that all the star formation occurred in H2, then yes, that will give you a very high efficiency, which is misleading. So basically what we're saying here is that there's not much CO dark H2, but there's a lot of CO dark H1, is what we're saying. What's that? Yeah, that's where this will be most important.
Okay. Ida.
Hi, nice talk. I have two questions. The first one, in your molecular outflow part, is there some kind of normalization to your dust to gas ratio? Because I think your dust to gas ratio always starts from 1.
Yeah, it's normalized to Milky Way.
Okay, thanks. And the second question is, in the first part of your talk, you mentioned that you treat ASIAA chemical evolution in the hybrid strategy.
Right.
Then in your second part, which part of the hybrid strategy do you put your dust evolution mechanism?
Oh, it's in a simulation.
It's in the simulation.
Right. You cannot do it in post-processing because the time scale for these dust processes is actually very short.
Then how does that impact the carbon budget in the post-processing of the carbon cycle?
So it will significantly boost the carbon chemistry, right? So we do the dust evolution on the fly in a simulation, but then in post-processing chemistry network, we then use that dust to gas ratio to calculate chemistry. So in post-processing, you actually have a lot more dust if you consider dust growth.
Just a thought experiment. Nice talk, by the way. Since you're starting, so that this is related to the last part of your talk. Since they're starting to form dense gas and forming dust, H2, if you follow the cloud long enough, does it start to form stars? And feedback, you blow away the clouds and the cloud
Yeah, that's actually very interesting. I have to say again that we cannot address that question. Not yet, not in this because what I didn't mention is that we didn't include self-gravity in those cloud crashing simulation. So the cloud become denser because of compression, not because of gravity. Right. So the dense gas form not because they collapse, but they form because in order to remain pressure equilibrium, once you lose the thermal support, you just need to go up. So, but I see your point. In principle, you can actually form stars because there's nothing to.
Things will actually be faster. Because the self-gravitating and cloud actually form faster.
So assuming that the Jeans mass is, so assuming that the cold gas is actually gravitational unstable, then they will form stars. So I'm pretty sure if I include self-gravity for a large enough cloud, they will form. But if the cloud, so usually people ignore self-gravity in these kind of simulations, it's because these clouds are very small. Their Jeans mass is actually very large.
Getting
I'm just a bit confused how you increase the dust abundance by dust groups. By dust groups, what exactly do you mean? Is it condensation from gas phase or is it from accretion from solar?
It's the first one. It is accretion from the gas phase. So we do not consider coagulation or any other processes that will change the size of dust. So.
good. Ivan.
I might have asked you this before, but do you have predictions on the dust temperature and the outflow?
Dust temperature.
And how did it evolve? So I was
Dust,
wondering if it ever get significantly hotter than the ISM dust.
I actually expect, so we do have dust temperature, but actually expect the dust temperature to be low because there's no UV radiation to heat the dust up. There's like metagalactic UV radiation,
Yeah.
but
Do
that's
you expect it to go higher in the beginning and then cool down to below ISM dust temperature?
why should it go higher initially?
I have no idea. So this it was just a guess. When you launch the outflow, there is some energy input.
So the most dominant heating mechanism for dust is really just photoelectric effect. So it's really driven by radiation. So I don't really expect. So of course there's collision between dust and gas, which can presumably heat up the gas, but that requires very high density. So usually it's not that efficient at these densities. So if I have to guess, I would say that they actually are colder than in the ISM.
Okay, great.
Yeah.
Because
Is it-
we have stochastic heating by the collision with the free electrons in hot gas in
Stochastic.
process.
Right, in hot gas,
Yeah.
they are just sputtered, so there's no more dust.
It
Right.
takes time to sputter.
Sure, but okay, but it's basically the same effect. It's just collision. But if you don't destroy dust, then okay, I see your point. Yes. So in actually in the hot phase, it can. Now I take it back. It can actually be heated up, just because how hot the temperature is. So you don't need to go to as high densities. Yeah.
Would be very super interesting to see if you can predict the evolution, the dust temperature evolution over time, and also spatially. Maybe there is some co-component in the middle, and then some hot shells.
And why is that super interesting?
Well, so if they're hot, then they emit strongly, right?
Oh, right. So you want to know if we can see it. We can see the
It
effect.
just need to be 5K hotter than the ISM to be outshining, and which is probably ruled out already.
I see.
There is observational implications.
I see. Okay. Yeah, that's actually doable in our simulations. So I'll check later.
Okay. Very good. Nice talk. So that's if you have a question, you can go downstairs and check with Chia-Yu's office. And that's a nice job again.
Thank you.